let's look at example 12.1. So this, we have a cantilever beam fixed at one end, okay, point B, and at point A here, a vertical load of P, of magnitude P is applied at this point, sorry, point A, point A, okay, and then you're given that this is X, okay, X-axis, and this is nu, okay, mu is a deflection. So if you apply load like this, you have to visualize that this cantilever beam will deflect like this, alright? Which means that there is no deflection, there is no slope at this point because it's a fixed end, and then it will deform until it reaches the maximum deflection at A, okay, the point that you apply the load, alright? So this is what we call as its elastic curve, right? And from here you know that from this point A initially to this deflected point A prime, then you have this nu A, okay, nu is the deflection from the original position and the deformed position, alright? And also you know that, yeah, I mean, this is just an extra tangent to this, okay, call this theta A, okay, and this theta is basically d nu over dx, right? And then you can define this direction as x from point A left to right, okay? So the question asks you to find what is the elastic curve, the equation of elastic curve, and you are given that EI are constant. Okay, EI is flexure rigidity, EI is constant, right? As we have discussed in the lecture, basically we have three equations, okay, for the differential elastic curve, which are EI, force derivative, and this is equals to Wx, isn't it? And you have EI, third derivative of deflection equals to Vx, isn't it? And then you have another one which is EI, second derivative of deflection over squared of x is mx, okay? So from here it is quite clear that you don't have W, right? Because this is a concentrated load P, not distributed load W, so you don't have this. You can use V and M from this because you have learned in chapter 6, 6.1 and 6.2 that if you cut and you analyze this beam, you can find your shear force and bending moment diagram, right? So what you can do is you cut, okay, cut. For instance, the left, you cut somewhere, take the left section, okay, instead of the right, because if you want to take the right, then you need to find what are the directions first over here, okay? And then you have, at this point A, you have point load P, right? First load P, downwards, and you cut, and this is your X, okay? From X equals 0 to X equal to L, okay? Usually it is given like this is L, alright? And what happened at the cut section, the section that you cut, you have what? You have bending moment, and of course you have the shear force V, right? So from this, if you do moment about this point, again go back to 6.1, again that's why it's very important. You do moment about this, you have M plus Px equals to 0, right? M plus Px, okay? So positive Px equals to 0, and M is positive, so M equals to minus Px, alright? Okay, in this case, so this is the equation for bending moment. I mean, for throughout the length, right? Because if you cut anywhere, you have the same. You have the last section. It is the same free body diagram like this. So this M equation is applicable to throughout the length, the L. Okay, throughout length. So this is the M. Okay, the moment equation with respect to x. So now can you see that this one you can put it here, right? And then you have this, you integrate, and then you can have your new in terms of x is your elastic curve equation. Okay, that's the idea. Okay, so this is one more thing. This M, you see, remember we follow the positive sign convention. Alright, so M is like this positive, nu is like that positive. Alright, because if you assume M equals to here and then you get M equal to Px over here, it won't be right. okay, we'll have problem because now we are in these equations we are using consistent sign conventions. Okay, and positive this way. Okay, right? And V positive, you use V positive, causing the section to rotate clockwise. Right? Okay, so we go to this M. You plug this expression into this. So what you have, you got this EI, second derivative of nu, which is the vertical displacement. Okay, remember in this equation, in all this definition, nu is going upwards. Okay, positive nu of deflection going upwards. The x, okay, x is the location, okay, equals to mx, which is minus p x. Okay, how do you get this nu? So you need to integrate, right? You do integration. Integrate here, integrate there. So EI is constant, right? EI is constant, so it's fine. Just leave it as EI, okay? But here, when second derivative you integrate, it becomes first derivative, isn't it? Equals to, how to integrate this? This simple polynomial, px squared over 2. Isn't it? And you have this constant, plus C1. Why C1? Because that's the first constant, right? Okay, you integrate once, you got this du over dx, okay, in the equation. But this is not the elastic curve, right? The elastic curve should start with, elastic curve basically is nu x. So you integrate one more time, right? So what you have is, you will have EI nu, okay, now this is your, okay, if you express nu equal to the rest, and that one is your elastic curve for the deflection, okay? So what happened here? You have px cubic over 6, don't ask me why, this times 2, okay, plus c1x, okay, plus c2. Again, this is basic, very basic integration. Cannot do this, go back to calculus, right, maths. So basically this is your equation, right, for your elastic curve. This nu equals to, of course you bring EI fraction rigidity to this side and then the rest, right? But this is incomplete, right? The reason is because, forget P is constant. That's fine, you can be any value, just put it value later if you are given P. But how about C1 and C2? C1 and C2 are the integration constants. So you need to find this C1 and C2 to make, to complete this this equation. So how do you do that? That's why on this beam you need to know what are the boundary conditions. Okay. So now we go to boundary conditions. What are the boundary conditions? You see, at point B, right? At point B, nu B equals to 0. Okay, sorry. At point B, x equals to L, nu B equals to 0. Point B is x equal to 0, L, right? X equals to 0, x equal to L. So at point B, x equal to 0, x equal to L, and nu B is equals to 0. Alright? Boundary condition means that at that certain location, you know what exactly that condition of that boundary, this boundary, right? And another one is the same point at point B, which is x equal to L. What else you have? You have, because it's a fixed point, you have theta B equals to 0. Alright? So, for the first one, okay, x equal to L, yes. So, okay, so how do you do that? You put into this, okay, theta B is basically d nu over dx, okay. So it is 0, okay, for this one. It is 0 times EI equals to minus PL squared over 2 plus C1, isn't it? So your P1, your C1 equals to PL squared over 2. Is it okay? And for this one, so this is your first constant C1. So the second one, when at x equal to L, and nu equals to 0. So you have 0 equals to minus PL cubic over 6 plus C1x, which is PL squared over 2 times x equals to L, right, plus C2. So what you have C2 equals to, okay, this one PL cube, right, 1 over 2 minus 1 over 6 is 3, 2 over 6, bring over there is 1 over 3, isn't it? So minus PL cubic over 3, alright? So first integration constant, second integration constant, C1 and C2 bring back here, so you'll have your, let me just see this. Just bring it back here, so you have nu, okay, to make it more mathematical, mu x equals to 1 over di, alright, minus px cubic over 6, right, plus c1x, plus c1 is plus pl squared over 2x, right, what is it again? Okay, this one, and plus c2, which is minus pl cubic over 3. Alright, so this is your equation of elastic curve. Alright, so the question asks you to, if the question asks you to find what is this deflection or that one, just here x equals to 0, you put x equals to 0, okay, and then whatever you got, that one is your vertical displacement at this point. Even if you put x equal to L here, you will have 0 on this point. You want to find slope at point A, you put d nu over dx, okay? Now, d nu over dx over here, okay, with C1, you put x equal to 0, you will get your slope. And then if you, the same one, okay, the differential equation, even you can differentiate if you want, I mean, it doesn't matter, they will match up eventually. If you put x equal to L for d nu over dx, okay, you will get your slope here